Yes, it's going. All right. Hello. No.
Hello.
Have you seen that show Ground Floor? It's on TBS.
Oh, no, you should do like the Big Bang Theory fun with flags.
That was that Ground Floor is kind of like that. A guy had an opportunity as a financial management to be on a business show.
He was like, hello.
So the charts are showing a high. It was so funny. Anyway, all right.
You can post on YouTube as well for your teachers.
Okay, kinetics is the study of the rate of a chemical reaction. All right, we've looked at stoichiometry is looking at the law of conservation in a chemical reaction. Equilibrium is the balance of a chemical reaction. Thermo is the energy involved in a chemical reaction. And now kinetics is the speed of which we convert reactant to products. All right? And in a general sense, when we talk about kinetics, we're talking about rate, and rate is change in amount, in a general sense, over change in time. All right? And so we can use any units that reflect that. We could say grams per hour. We could say pounds per, millisecond. That is, they don't have to be these units, because that's another thing they do on the AP exam. What could be units of this? And you're looking for, Ms. Mullane said it was molarity per second, and I'm not seeing that, So in a general sense, a rate of reaction is looking at the change in amount over a change in time. Now, the accepted values in kinetics are then molarity, change in molarity over change in time as seconds. So we're looking at units for rate of molarity over seconds. All right? Units are huge in kinetics. A perennial mistake is screwing up the units. All right? But, so especially if you see them written like you're, what in the world is that? That -1. That's just because it's a pain in the butt on your computer to try to get the M and a line and S. All right? So it's easier to do that. All right? So remember that. You can see units in a variety of ways. All right, now there are 4 factors, four factors that will affect the rate at which a reaction occurs. First of all, it's the state of the substance. All right. Obviously, gases are going to react more quickly than a solid or a liquid. Okay, and that's why a lot of times we need to ionization energy. Think of that. Ionization energy and electron affinity. The first thing that you have to do is get the substance vaporized. You have to get them as a gas. And then once they're a gas, you look at gaining or losing an electron. All right? And that's a good thing. We don't want everything around us that's a solid gaining and losing electrons. We could have things blowing up around us. It's a very good thing that most of what we have around us is a solid, because solids are unreactive. But boy, we get them to a gas state and then that changes. All right, so one thing to look at in a chemical reaction is the states. If you're looking at speed, which could explain why it takes a diamond so long to decompose to graphite, because you're looking at a solid going to a solid. Of course, if a diamond were a gas, it wouldn't be nearly as nice. All right. The amount of a substance. Obviously, if reactions got to react, there better be some reactants. If I've got a drop of gasoline on the desk, let's not go there. That was a bad analogy. And then temperature. Temperature, and this is always, well, usually, yeah.
Does the reaction go faster with a little bit of substance or a lot of substance?
A lot of substance.
Okay.
The more you have, the quicker it goes. And we'll see why in just a minute. We're going to get to why. If they've got to react with each other, there's got to be some there. All right. And they got to hit each other and react with one another. Yes?
Is the rate going to be constant, or is it like more like if the amount of substance affects, yeah, like is it, yeah, okay.
As we run out, it slows down. Excellent, excellent application of that. Because you're going to see later on that we're going to look at initial rates, because when we initially start is when what? We have the most, all right? We're not going to say 5 minutes into the reaction, let's start looking at it. All right. How many of you have ever had to run the mile in gym and you start out great and you start petering out? You're going, oh, what am I thinking, you know?
That's every time.
Your initial rate was quite well. Oh, I should be out for the track team. 2 minutes later, no! Go out for archery or bowling.
Oh.
Okay. And then now the reason. No, let's we'll come back to that temperature picture in a minute. Let's just go over the 4 things that affect, and we will then go back and explain these graphs. And the presence of a catalyst. You know, that is used in nature to speed up reactions. You know, if I put hydrogen peroxide on the table, it is decomposing into water and oxygen. If I throw some potassium iodide in there, it just bubbles up, right? And I think we've seen that in a video or whatever in honors chemistry. All right, so the question is, why do these factors affect the rate of reaction? All right, and that is something, anytime we observe something, and these are the observations, we have observed that for some reason gases react more quickly than a solid. That the amount of substance we have increases the rate at which they react. The rate, actually, the speed at which they react. The temperature affects the rate at which they will act. And for some reason, why does putting a catalyst speed up a reaction? Just throwing something else in, wow, all of a sudden it speeds it up. The answer, anytime we have observations, we come up with a theory to explain those observations. And this theory is called the collision theory. And it has 3 states to it. Reactants must collide, they must collide with sufficient energy, and they must collide with the correct orientation. And I showed you guys, I think, a video of this last year. It is called Collisions and a Date for the Dance. Remember that? Or didn't you guys?
I think we may have mentioned it.
You gave us an analogy about like dances and covalent bonds, but you didn't show us a video.
Yeah.
There were,
Do you remember me and Owen?
Yes, I fondly remember. I probably shall never forget this one.
yes.
First, I want to show you a short video on the question of, does amount affect the rate of reaction? Let's look at a short video on that, okay?
All right, so we have some steel wool. Now steel, made of carbon and mostly iron, does burn, okay? So a little bit of activation energy, it does burn. Steel wool. Now there's carbon in steel, so that's predominantly what you're seeing, but it will burn. Steel does burn, okay? In fact, you take steel and you make it into smaller pieces, you can get a terrible flame, as I'm having here. Okay, so what I'm going to do now, assuming this has anything, is I'm going to put some oxygen in my flask.
Now,
I'm going to
that was, the steel wool was iron plus oxygen. So he's looking at the oxygen, which is 20% in the room, and now he's increasing the amount of oxygen.
Okay, and assuming my lighter works, we're going to put some of this steel wool, okay, into this flask, and
Is
now,
that what our video is gonna sound
why was
like?
the rate of reaction so much faster? No, it wasn't a catalyst, it's part of the reaction. Well, think with me for a second. If I put more dancers on a dance floor with the same space, what's going to happen to the number of collisions? Yeah, they're going to increase, therefore the frequency of effective collisions increases. So I increase the rate of reaction by increasing the concentration of the oxygen. The reason why you don't smoke in a hospital is that that's what would happen to your cigarette, especially in a room that's been pumping a lot of oxygen. The rates of reaction are much, much faster if you've got more reactants. Okay? So,
Alright, so that is a great demonstration of how an amount, increasing concentration increases the rate at which that reacts. Okay.
9:46, it is time now.
Oh, no.
I'm taking a video of a video.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk to her class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help ensure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, so I want to see you all run out of this room with your books and be thinking prom. Well, then you don't have to. I would travel in packs.
Travel back.
Like me on the inside, so I'm first.
No, I'm not gonna make it to where I run to the right person. I'm like maneuver.
Now we know what our hallways are saying there, like the
Is
paper
it
is
like
like
a
a catalyst.
Yes.
But no,
Matchmaker,
Okay.
central matchmaker.
And I think the central, they've already done this. They've shrunk the size of the hallways.
There you go.
And the amount of people
And
that
they've
push
Crazy.
put a bunch of 6th graders in our way.
All right, so now I've included a little diagram here. If we look at that diagram as HCl reacting with C2H4, all right? And we're hoping to get C2H5Cl, all right? Now, to get that to happen, the collision theory says 3 things must occur. First of all, the HCl must collide with the C2H4. In other words, there's got to be contact. If they don't contact each other, there's no reaction. All right, but that's not enough. They've got to collide with sufficient energy. This has a particular name. It's called activation energy. It's that nudge I told you about, right? It has a symbol E sub A. Remember I told you it doesn't mean that it's endothermic, that I had to apply energy. Activation energy says everything needs an initial nudge. Putting a match into gasoline is the best example of that. That match is the activation energy. That's the energy required because if I have a barrel of or a bowl of gasoline sitting on this desk, it is colliding with the oxygen in the room, isn't it?
That's what we see.
All right? The thing is that the collisions don't have enough force to have combustion. All right, so how do I get them to have more force? I heat them up, let them move a little faster. So I light a match, and that match then, in the area surrounding that match, is energizing the oxygen and that gasoline. They're moving around enough, and then wham, that's all we needed. All right? So sufficient energy. And then the right orientation. Is it I before E or, did I get that right?
It's
I before E.
Yeah, it's
Except after C, but that's
a lie.
It's
It's a myth.
All right. What does that mean? And that's where I showed you that drawing.
Let's look at it.
Okay? That the bottom one is obviously the HCl. Apparently, the orientation is that the H must hit between the 2 double bonded carbons. This is, let's look at this. This is what C2H4 looks like. It's a nice non-polar hydrocarbon because of symmetry. All right, and then we have hydrogen and chlorine. Okay? Chlorine is the bigger one, isn't it? Because it's an anion. Hydrogen would be, Well, not really an anion, that's molecular, all right? Okay, so what they're saying is not only do these have to collide, they have to collide with sufficient energy, and they must collide where the hydrogen hits that double bond. All right? You know, have you ever backed into somebody? You don't really acknowledge, you say, oh, excuse me, and then you go on, right?
I've gotten a car.
It's a little bit different if you front into somebody. Whoa, you know, isn't it? I mean,
Hey,
just,
wanna go to prom?
yeah. You know, the collision's a little bit more personal when it's front to front, where if you just nudge your shoulder or back into each other, you know. So it's the right orientation, and apparently, according to this drawing, if this hydrogen hits this hydrogen, nothing happens. If this chlorine hits the double bond, nothing happens. All right, so we have to collide. We have to collide with sufficient energy and with the correct orientation. Right? When those three things happen, we will have a reaction. All right, so now let's go back and look at those factors. If this is it, this is the theory, then let's look at this. How does the state of a substance then, using collision theory, if I've got solid HCl or I've got gaseous HCl, using collision theory, why would that matter?
The solid can't move around as much, so the gas is
Less
like reacts.
collision, more.
Yeah, less collisions, right? And then less surface area also. So several factors. If it's not moving, it can't collide with much energy, and if it's attached to several other HCl's because of the solid, that orientation is going to be next to 0, all right? So we're really going to reduce the speed of reaction if we have a solid as opposed to a gas. Okay. Using collision theory to explain that. All right, the amount of substance, we just said that. No, the amount of substance. Why is it that the more we have, the faster the reaction takes place?
Surface collisions.
Collisions, yeah, and the probability, more probability of getting the correct orientation if you've got more hitting them. All right, so it's kind of a statistical thing, isn't it? You know, if you've got a 1 in 10 chance of winning the lottery, and you've got 1,000 lottery tickets, you've increased your odds of getting cabinship. If you have 1 lottery ticket, all right? So the more we have, the more collisions we can have, and the more correct orientation we can have. All right, so that is one thing that we do is, and in kinetics, we always look from the perspective of the initial rate. Because for one thing, it's a reference point. They'll all be similar to this, and this is all when they happen the fastest. You know, we've got an hour-long class. We can't say, we'll wait 5 minutes into this, and then we'll start timing it, you know. You're not going to be out in the hall getting a collision, so you wouldn't want you to pull you away from there. All right. Okay, the temperature. This is a Maxwell-Boltzmann distribution graph. You need to be able to interpret that. Now, what the Maxwell-Boltzmann distribution is saying, let's say you've got the same number of particles. Let's say we've got 100 particles. And look at the one that's at just the capital T. That would be at a lower temperature. Okay? Energy is on the x-axis, so we're increasing energy, increasing the temperature as we go across. At a lower temperature, the graph, the curve is always more homogeneous and large, all right? So at a low temperature, we see that the majority of the molecules are in this temperature range, in this energy range. And if the activation energy, all right, see that line they've drawn? That line represents the threshold energy they need to have a successful collision. All right, now look at T. Okay, the majority of the particles do not have that. Now, the curve of T plus just upping the temperature just a little bit. Look what it did. Okay, it spread this out more, didn't it? It came lower And then what we did is we're shifting. We have much more molecules that have sufficient energy that cross that threshold. So what happens when we increase temperature is this gets more spread out. It's not as nice a rise. So what that means is it pushes, this is the same number. This is my 100 molecules. Now of my 100, I've got a lot more just by raising the temperature a little tiny bit. All right, now notice the temperature isn't the height of the curve. The height of the curve is the number of particles. And so when it's high is when it's a low temp, okay? More number aren't there. As we raise the temperature, we have more disorder, don't we? So they spread out more. You can use that from an entry piece. You know, it's not as nice and crisp, okay? It's gonna spread out more, and we're not gonna go to that height. But that height represents the number, not the temperature. Sometimes, perennially, a confusion on Maxwell-Boltzmann is say, which one would be at 600 degrees? Oh, well, it's the one that's taller. No, the height is not the temperature. This is, notice the y-axis is the number of particles, and it's as we increase the temperature, what happens. And what you do is you flatten out and spread them out the more you raise the temperature. Okay. Maxwell-Boltzmann is also on speed. So if you're comparing heavy molecules to light molecules, the heavy ones are going to be over here, more homogeneous, not moving around much. The lighter, they're going to move more, so they're going to spread out. So those are the two interpretations you need to know with a Maxwell-Boltzmann distribution curve. All right, the presence of a catalyst. All right, on a graph, and you're really going to need to be able to interpret this graph, but we'll get into it in much more detail a little later. So let's just introduce it to you, and this is just the reaction graph. Just saying, in the course of a reaction, here's what happens. All right, we've got these reactants. By the way, is this endothermic or exothermic? Very good, because we start at a high energy and we end at low. But this is also a reaction that really needs a nice little nudge, doesn't it? This represents what nudge we need to give it. This is the activation energy. Okay? When we give it this much energy, that's when it happens. All right? This would be the equivalent of I've got my gasoline and my oxygen. Right? And it's sitting there. Not much is happening. I give the match, then it goes. All right? Actually, on that one, it'd probably be more like this. Woo! Okay? Doesn't take much, does it? And it really goes. All right, so you can kind of compare things that need a lot of activation energy and don't give off much versus don't need a lot of activation energy and will release a lot of energy. So being able to look at these energy profiles is what they're called. Now, what will happen with the catalyst, and this is where you'll need to draw this in on your graph, is you put this dotted line and they create a more favorable environment for collisions. Either they affect the reactant, like, remember we had this and we said it was important that the hydrogen attack right here. All right? Well, what a catalyst will do is maybe change the nature of this to where this hydrogen can hit other places and still be effective. Okay, if all of a sudden you don't have to hit just here, but you can hit here, here, or here, does that speed up the reaction? You bet. Okay, so what a catalyst usually does is change the nature and make it different. And then it's not involved in it. It is just, it goes in, it helps, and then it steps back. all right? It can be an intermediate species, which will, you kind of create something that isn't really this. It's something different, but what it does is it helps this H attack different places that are easier to attack. So it really affects the orientation. It gives you other areas of hitting and getting successful, and in doing so, it can really speed up the reaction. But this is what an energy profile looks like if it is uncatalyzed. Is that S or Z?
Well, it depends on whether or not you're British.
All right, and this would be catalyzed. Right?
Should catalyze as a Z. Yeah. Yeah.
But never.
It's just like gray and gray.
All right? Anyways, the exam likes you to show the difference between a catalyzed reaction and an uncatalyzed reaction. It's always lower. All right? And we'll get into that in depth, but that's another thing. That's usually worth a point or two on the AP exam. Show the difference, point D. And that's one of those where you gotta go through, because that's the easy one, all right? Here you're going, show the differential rate law for the blah, blah, blah. You're going, what? D, show the chart, catalyzed and uncatalyzed. I can do that, all right? So that's where you need to skim over those. Where's that easy one gonna be? Okay, so that I just wanted to introduce kinetics to you today. And we will actually stop there.
Yay.
I'm gonna do something different for the homework on this. Is I'm gonna go through the AP exam, and your homework is gonna be about 5 kinetics free response. And then instead of the extra credit, those multiple choice will be your homework, and I'll come up with a different extra credit. So your homework will be multiple choice and free response, and we'll see if that doesn't help more when you're taking the test that's multiple choice and free response. Maybe there will be more of a connect there.
For the energy diagram,
And
can
the
you
next